Okay, you might notice the screen looks a little weird. I actually recorded this video, well, the whole thing, um, on task 2, but then I was rewatching it, as I do with all of these videos. And I noticed halfway through, or a little less than halfway through, my audio just goes out. I'm not sure why. I just stopped recording my audio, but it did. And so I'm going to just um, I have the full recording, so I'm just gonna play the recording, and then the sound will be on for part of it, and then when the sound stops, I will step in and I'll talk over the other part. So yeah, without further ado, let me mute my mic. All right, today is just a continuation of what we started last time, Quantum Open Source Foundation application, what not to do. That's a joking title, so I'm not saying you shouldn't do this. I'm pretty sure all of the information here is correct, so I hope it is. But it's just a joke title. And so today is task 2, and that means quantum error correction. Very simple stuff. There's a lot of work in quantum error correction that I do not know anything about. But this is, the basic sort of stuff, not any of I mean, I don't even know what the new papers are about, but I see them. They're on my little archive radar, but I don't read them. So the first part of this task is simply to prepare a Bell state that we're going to be messing with. And so, we have our typical Bell state here, which is 2 qubits, Hadamard on the first, controlled C0. This creates the entangled state 0, 0 plus 1, 1 with that is equiprobable. And so this is, iconic, quantum computing 101. So we'll see how to do this in Cirq. This should be pretty straightforward here once again. All of this question, the exact question is actually in the at the top of the file, so you're welcome to look at that. So we create the qubits, 2 qubits, the simulator, the standard bit string. This just converts a string or an integer array into a bit string, and so that's unimportant. So we create our Bell state. We make our circuit. We append a H to the first qubit, C0. We measure both qubits, and we measure it 100 times, and we get the results. So if I go over, and I do here, just pause, and I go over and I show you the screen. Ooh. Let me zoom in. I realize this is probably helpful to zoom in. There we go. That might make it easier to look at. So we can run the code. This should not take very long. And we can see perfect. 0, 0, 1, 1, almost equiprobable, well within the expected standard deviation of variance. And that's the Bell state prepared. That's pretty quick, pretty easy to do, not talking about it a lot. So yeah, that's pretty much it. So now we have, wrong screen. So now we have to get to task 2. Task 2 is to artificially create errors. So there's 3 types of errors we create. So we create the Bell state, and before the C0, before this is applied, we have some errors here. And they're just artificially induced. The simulator's perfect, so no errors there. And so we have either no error, so we randomly we have equally probable chances of placing on either one of these spots right here on both qubits, either no error, the identity gate, bit flip error, the X gate, or sign flip. That makes it the negative. If you put a Z, there, it would be 0, 0. Ooh, my DPI is way too high. 0, 0, and it could be minus 1, 1. Screw 2. And so this is pretty straightforward. if we get into the code, we can see to create the error bell state, we create a circuit, we apply the H gate, remember, because these are after the H gate, and then with equal probabilities, we simply either apply, ooh, what just happened? Okay, I don't know what just happened there, why it changed colors. We either apply the I gate, the X gate, or the Z gate. And then we apply the C naught, and then we measure. And so this is the error, bell state that has some error. And so to quantify this error, hold on, I'm gonna make a quick edit. Okay, I just made a quick adjustment to show the errors. So we make the error circuit and then we test it. So we can see we create 100 different error circuits. We run each circuit 10 times, and we can see that the all right, so this is where the original audio cut off, and so now I just want to talk over it and sort of asynchronously do this. I mean, I just recorded, so I know everything I'm saying, but here we can see that we can categorize the errors because they're going to be 0 1s or 1 0s. And so remember, because we're expecting 0 0 and 1 1, any errors are going to be able to form 0 1 or 1 0. So we can get the total number of errors and get the error rate by dividing the total number of errors by how many runs we did. And so we can see that we expect this error rate to be around 30, well, not around, exactly 33%, because anytime there's an X, remember that the bit flip error is what we're concerned about. So anytime there's an X, which occurs in 33% of cases, we would expect there to be an error. So we expect the error rate to be about 0.33. So I'm going to run it again real quick, and we'll see that we can see, okay, yep, error rate 0.3. That's pretty much expected. You can see I'm canceling it. I'm hitting Control C here just because I don't want to see the next part of the circuit. And so I do it again, and we'll see 0.3 something, 0.322. Yeah, so that's pretty close to the exact error rate is 33%, because remember, that's exact, that we're sort of predefining that error rate almost. And so now we can see that the error rate is around there. It's not going to be exact because it's an approximation based off of sampling. So now that code was all added, so I'm just going to adjust it slightly, get rid of the input, and we can go on to the last part of the task, which is going to be the error correction part. So with the bit flip code, you can see it's presented here. You can also see on Wikipedia, they have a pretty good overview of it. The bit flip code is a form of error correcting techniques for errors in the X, of the X kind. And so we can see the general framework here, right? We have the qubit, and this is a single qubit it operates on, much like in a classical case where we have redundancy bits. We have multiple bits for a single qubit, and what I'm highlighting here is that we do this before and after some sort of noisy operation. And so we apply, we have two known 0 qubits, and then we apply the C naught gates controlled by the original bit on both of them. We go through the noisy op, and then we do that exact same thing again. And so we can see at the end of that operation, because at the end we undo the the operations we did, remember, because applying the C0 gate twice just undoes it. However, excuse me, because there's a chance for noisy operations, there's a chance that that bit flip code isn't just undoing it, but restoring it in that sense. And so, you can see the setup is almost exactly symmetric. We just look at the error and then we do the result. So what I'm showing down here is that, right, we know that you're applying this gate twice, which gives you the identity, so it undoes it if there's no if it's noiseless. So we're considering a noiseless case here, right? So the noiseless case is that the 2 qubits do the 2 C0s, and then no noise happens, and then the C0 happens again. And so that exactly cancels it out. And so we're left with the state 0, 0, and then our unknown qubit. And so we can see that controlled C0 has no operation because the inputs are 0. So we can see that in the case of no noise, this does nothing. And what I was drawing up there is just a note on notation. And so in the error-free case, the C0s undo each other and the last operation has no effect. So we can see that clearly this works in a noiseless case, but the case we're really concerned about, obviously, is the case with noise. And so maybe I can skip this up a little bit. Not that far. Yeah, so we can see in the noise-based case, just pause it here. The noise so this is whatever this is, right up here. We're getting the it's having some or none impact. It's doing something with these qubits, and then that is if this changes, right, this operation is not inverted. So if this goes in as a 0, right, does nothing to them, and it comes out as a 1, then it will flip these bits. So the operation is sort of inverted, not inverted because that's bad, but the opposite of it is done. And so then if these are both 1, right, if this went in 0, error, bit flip, and these are both 1 now, then this will actually control this and flip this qubit back. And so we can see that the basic case of this bit flip code, and we can see that when there's no error, these two cancel out, and they sort of have this effect of regularizing this change, and then impacting that last gate is for actually making the change to the qubit that might undergo error. So now we're going to go over to code. So we can see that to create the code here, the bit flip correction, we first create the circuit. Remember, we're going to create about 1,000 of these circuits, and then we go through and we remember each one of these bit flip codes only applies for a single qubit, which therefore means that for every qubit we have to do this bit flip code. So we actually have 2 sets of 2 additional qubits for each of the 2 qubits in the going into the Bell state. So we then do the C0s. Sorry, I was just adjusting my microphone. So we do the C0s, and then we can execute the Bell state. So the C0s, remember, are just to establish this this first setup, right? We're just checking basically what the initial setup of the qubit is. And then we get into executing the Bell state. It's the same as above: the Hadamard gate, the error, and then the C0. And then we can, I'll just skip ahead here. We can skip ahead and see that the ending is the exact same as the beginning, with one additional sort of influence, right? So we undo or do the operations, the C0 operations on each of the qubits at the beginning, and then we do the controlled operation, and we only measure the last, or or the first two really, the Bell state qubits, not the error correcting qubits. And so then we can print out an example circuit, note that every single circuit is different, and print out the relative error rates, which were calculated the same way as above, right? We get the number of errors, which are measurements that aren't 0, 0, or 1, 1, and then we divide them by the total number of measurements. So if I run this code, which I will hopefully do, what's going on? There we go. So we can see, first of all, we'll get the Bell state output, which is just, boring. Then we get the error rate from the last discussion, which is around 0.33, and then we can see the circuit. So the first one is just an example error circuit. The second one is the bit flip corrected circuit. So the first error circuit we can see is a double phase circuit. Ooh, I don't know what just happened there. And the second circuit has the bit flips. And so we can see for the second circuit that the measurement operations are only on the two Bell state qubits. So we can see, this is sort of, ignore these X's, right? This is the Bell state creator right here. And so then we can see that we're applying, so those are the errors I'm highlighting right now, but we're applying the C-naughts before and after. You can see it's very symmetric almost. And then we're doing the multi-controlled Q C-naught above. And excuse me, what I just showed below is that it just so happened that both of these circuits had the same exact errors for both qubits. Below, I was just showing that they're not necessarily always the same. So you can see that each qubit in the Bell state has two sort of backup qubits. And then I'm highlighting the first C-naughts right now. And we can see that, this is pretty much exactly as described. We're just repeating this process, this code for two qubits, because there's two qubits in the Bell state. So we can see that the error rate, which is the default, the error rate of just a normal circuit, is almost exactly 33%, which is what we expect it to be. But the big takeaway is that the bit flip error rate is 0%. We've successfully eliminated all of these bit flip errors using this code, and so we don't care about the Z errors, because those are sort of phase changes, or sign changes, I should say, that don't impact the actual computational basis measurements. So all we have to do is do the sign, do the bit flip code, and then you can hear my cat yelling at my door, and then we can see that this perfectly eliminates all of the errors. Of course, this is okay. Let me go get my cat real quick. Okay, and that was recording the whole time. Okay, so sorry about that long pause, I guess. But we can see that the bit flip rate, error rate is successfully lowered, and I don't know why the screen is taking so long. Okay, so that's the takeaway basically, is that the bit flip code worked, and that this task was successful. And next time is quantum circuit simulator from scratch. I'll probably do a another intro to QC video before that though. Remember, the code's available, and I put all of the questions in the code, so check that out. Yeah, that's all.